Good morning, everyone. Thank you for joining. I just want to let you guys know that we will begin in about 5 to 10 minutes. We just want to make sure everyone is on and they are connected properly. If you guys have any questions in the meantime, feel free to put them in the chat under the control panel. Thank you. Good morning, everyone. Thank you for joining us. We can go ahead and get started. This is a refrigeration diagnostic webinar. My name is Carly, and I will be your host today. John, if you want to go ahead and switch over to the next slide. Thank you. Yeah, like I said, my name is Carly. I'm part of the marketing department at Intertech. During this webinar, we just suggest that you guys take plenty of notes, submit as many questions as you can. John will be going through the questions periodically throughout the webinar and at the very end. If you guys don't get your questions answered, shoot him an email, and then he will answer them that way. And then if you miss anything on this webinar or need to get additional information, you can go to our Intertech USA site and view the webinar again on our YouTube page. There should be a link on the front. And then you can email John if you guys have any additional questions. Yep, that is all for me. We can go ahead and begin.
So I was muted there. We'll go ahead and get started. Again, John Pendleton, I'm sure some of you guys have already sat through these webinars, so you've probably heard me before or maybe even seen me in person. If you do need anything, you could email me, or you can also email training@intertechgeo.com. You can give me a call. The first number there is my direct line, and the second number is back to tech support. So if you call that second number, you can certainly ask for me. So basically what we're going to cover today is we're going to look at the pressure temperature relationship. We'll look more, not really too much at the expansion device, although it does play a part in what we're checking. So we will cover a tiny bit of it, but mainly we're going to be covering the superheat and subcooling calculations and what they mean and where to take the readings. And we'll go through at the end a few practice exercises so you guys can kind of see on a refrigeration diagram of where those readings are taken and what they truly mean and what it kind of says about the system. So basically, the key to the refrigeration system is the refrigerant temperature pressure correlation. So all of our systems are using 410A now, which is pretty common. You may see a few other refrigerants out there, but normally it's 410A. Basically, the key to that refrigerant, it's going to boil at a very low temperature, and it's going to allow us to add heat to this system. And we can go down to about 20, 25 degree entering source water temperature is where we're trying. That's about how far we can go, which if you look at like an air source heat pump, an air source is going to quit, really producing heat at about 25, 30 degree outdoor air temperature. Obviously the thing about a geosystem is that we don't care about what the outdoor temperature is. We just care about the loop field, the water temperature. So instead of air temperature, we're using water temperature. So, as the air source cuts off at, 25, 30 degree outdoor air, ours, as long as our loop temperatures are above that 25 degrees, then we can still add heat to the circuit. This is a pressure temperature chart over here to the left. If you guys have done refrigeration, I'm sure you guys have seen these, have them on your trucks. I know I used to have a little notepad in my little front shirt pocket that would always have the refrigeration pressure temperature chart. If for some reason you don't have one, in the manual, there's always a pressure temperature chart towards the back of the troubleshooting stuff. So you can always look there, or you can always just look at your refrigerant gauges as well. But we will have to have this chart to do superheat and subcooling. Basically, this is basically the refrigerant and its changing of the state. So the refrigerant will evaporate and condense at different temperatures when under different pressures. So before the change of state, and this is showing basically water, so it changes state when it boils. So you can see before it changes state, when it moves from 209 to 210 to 211, we're really not transferring that much heat. So we're only raising it about 1 BTU for 1 pound of water before it changes state. At that change of state is where all the heat transfer takes place. So between basically 212 before it boils and 212 when it boils, there's a release of energy right there. And it's roughly 970 BTUs for raising it or changing the state of that water from a liquid to a gas. So before that change of state, it's considered a subcooled liquid. After that change of state, it's considered a superheated gas. So in subcooling, we want some degrees, make sure that we're transferring our heat, and then we want to make sure we've got superheat. So we're making sure all the liquid is boiled out and it's not returning to the compressor. We're not going to damage that compressor. So as we go along, you'll start to see, what these numbers mean and what you can start to look at. Now, I do want to make a quick assumption that when you walk up to a geothermal system, that you've already checked water flow and airflow. Obviously, if those things are out of range from what they should be, you cannot expect the superheat and the subcooling to be right. And some of these will tell you, hey, you've got a high subcooling and low superheat. I'm just kind of making this up. Don't quote me on this, but let's just say, that could mean that we've got low source water flow. So we've got to make sure that those things outside the box are working properly before we can really expect the refrigerant circuit to operate properly. It's just another product of what's going on in the whole complete package. So we have a few different types of refrigerant circuits, and we'll just kind of show you some of the things. This is a packaged unit, very common. You've got the air side, forced air unit. And you can see, number one, you've got your compressor. We've got our air coil, TXV, filter dryer, reversing valve, and our source heat exchanger. So these are basically the main components. This chart is in every manual. The chart in the manual will actually have some lines on it that you can put temperatures and things. But it is nice to be able to look at that little reversing valve to the left of the compressor there in that picture, and you can kind of see the path of the refrigerant in heating mode and in cooling mode. It's pretty common in the industry. They are almost always fail to heating mode. So if there's no power to the valve, it will be in heating mode. This is basically just a water-to-water refrigerant circuit. The only thing different is you've got a load coax, or it could be a braze plate, depending on the unit. But really the only thing different from a water-to-water and a packaged unit is just the load heat exchanger. Instead of running air over an air coil, now we're running water through a load coax. So it's not really a whole lot different circuit. It may look a little bit different, but there's really not a whole lot different going on. You still have your compressor, reversing valve, TXV, and your heat exchangers. And of course, excuse me, a filter dryer in the system as well. You can kind of see on this diagram, and like I said, in the manual, even on these diagrams, it will tell you, you've got a liquid line in heating and you've got a liquid line in cooling. So you've got to know, obviously, which mode you're in, and so you know where to check your superheat and subcooling. We'll get into that here in just a second. A split system is basically just, instead of having a built-in line set, you're adding a line set, but it's no real different than a packaged unit. The only thing that's mainly different in a split system is now you're going to have 2 TXVs in the system. So you're going to have one at the air handler and one at the compressor section. The one in the compressor section is always your heating TXV. And then the one at the air handler is your cooling TXV. Combo unit, now we get into a little bit more combo units, especially if you were new to them. You probably say, hey, well, hey, there's 2 reversing valves in the unit. The first valve in a combo unit is actually a directional valve, and it will choose whether the unit is in forced air heating or water heating mode. It does not run them both at the same time. So that directional valve is there to shift it over to your load heat exchanger. And the 3-way valve there is also energized to bypass your air coil, is what you're going to do when you're in water heating mode. But you still have just one TXV. So it makes it, pretty simple to be able to check subcooling on your TXV. And superheat never changes location of where it's mounted. So, excuse me. There are times when you will have a superheater in the circuit, and I just wanted to kind of show you where it's located. It's basically right off the discharge of the compressor, and it'll usually rob about 3,000 BTUs maybe. Some of our manuals will list numbers with that superheater on, but we would always recommend that you shut it off when you're doing some testing. Just one less thing to cause issues in your refrigerant circuit. You don't really have a whole lot of problems with the superheaters or them causing a whole lot of problems, but they will rob a little bit of heat. So we must use a expansion valve on any kind of heat pump, whether that be air source or geothermal. The cap tube, you can't adjust very quickly, so you can't have a real wide range of water temperatures in the ground loop. A TXV allows for adjustments, on the fly, basically. So, we're ranging anywhere from water temperatures of, 25 degrees down up to, 110. Now, we don't see 110 a whole lot, but that is a pretty wide range. So a cap tube really wouldn't work. We've got to be able to adjust the charge to maintain the superheat. Basically, the superheat protects the compressor. Again, we're normally operating between 25 and 110 degrees. And the only way to properly charge a unit, you could use approach and weigh a charge in, but superheat and subcooling is how you can always confirm it. So, like I said, yes, you can use the approach temperature to get your charge dialed in, but I was always double check with your superheat and your subcooling measurements. In our manuals, in the troubleshooting section, it will list what we recommend for the range of your superheat and subcooling. If for some reason you don't have a manual or you're not sure, a good rule of thumb for any of our equipment, it's a pretty easy number to remember, is 10. 10 superheat, 10 subcooling. If you can get it in pretty close to those numbers there, then your charge is going to be good. And, it's just a rule of thumb, and it usually works on any manufacturer's equipment. They're going to be somewhere right around there. Again, we give a pretty good range of 4 to 20 or something like that, but depending on the water temperature coming in. But just remember that 10 will put you pretty close to where you need to be. This is the TXV. We've already kind of covered that in a past webinar, so we're not really going to cover it too much. Although I will say that if you ever have a TXV stick, it's normally caused by something in the refrigerant circuit. There's not a whole lot that can break on the TXV to cause it to fail. Normally, the only thing that might break is the bulb. The bulb has refrigerant charge in it, and if it gets a little crack in it or rubbed up against a piece of copper or something, then it's going to release that little refrigerant that's in that line in the bulb, and then there's no pressure on top, and so the valve is going to stick closed. I personally don't know if I've ever seen a TXV stuck open. Normally, because it's got that great big spring on the bottom that'll always shove it closed, and then that's where it'll normally stick. That spring on the bottom is pretty thick and heavy, and so it's got enough force that if that piston gets, you know, that sludge on it, that it'll drive it up, but the bulb pressure doesn't have enough to drive it back down, so it'll normally stick closed. We're slide through this here real quick. Hang on a second here. I don't want to really cover the TXV again. Okay, here we go. Sorry about that. So superheat is defined as the number of degrees above the saturation temperature of the refrigerant. So for an example, if the temperature of the refrigerant is 40 degrees at 100 psi, you have a saturation temperature of 32, that would give us an 8 degree superheat. So you just basically do the math on it. And that's what we're doing, you know, when we check on the refrigerant circuit. We're looking at pressure, converting it to temperature, and then taking our line temperature and just doing the math on it. So, and we'll definitely cover all this here when we go through some examples and things like that. Subcooling is defined as the number of degrees below the saturation temperature of the refrigerant. So if the temperature of the refrigerant is 28 degrees at 100 psi, you've got a saturation temperature of 32 again. You just basically do the math, 32 minus 28, and that gives us 4 degrees of subcooling. So that's how we basically do it. Now, again, we'll look at this. When we have a correctly charged system, so we're going to have, let's just say 10 degrees superheat, 10 degrees subcooling, the TXV will adjust the orifice or the outlet to maintain the proper superheat. So we use this little image here to kind of correlate a TXV and what its job is in the refrigerant circuit and maintaining superheat. So it's basically like the expansion device is basically the outlet of the dam. So it's gonna, you've got your condenser, your high pressure is your reservoir in the dam, and then the TXV is gonna it's gonna try to maintain 10 degrees superheat, and it's gonna regulate that outlet of the dam, basically. So on a normally charged system, you're going to have normal flow coming out of the TXV. You've got plenty of refrigerant stacked up behind it in the reservoir, and it's just going to, you know, operate and maintain its superheat properly. So correctly charged system. You can see here we're showing 10 degrees of superheat and 6 degrees of subcooling. Now, if you look at this up here in the middle of the screen, that TXV, if you look at those lines to the left and to the right, you have liquid line in heating mode, liquid line in cooling mode. So we're in heating mode, so we want to check the heating side. The easiest way that I can tell you on a TXV of where to check the subcooling is the warm side of the TXV. There's a lot of piping going on in there, and you know it's in the bottom of the unit or up, you know, in the unit, and so it can be a little bit difficult once you open up that cabinet. Sometimes you get a little confused. Easiest way to know is just feel the warm side. There'll be a huge difference in temperature. So if you're not sure which side is heating or cooling for your subcooling, the warm side of the TXV. The superheat, there's a bulb on that TXV. Where that bulb mounts is normally about a foot or so off of the compressor on the suction line. So it's going to be a cold line. Just follow the bulb from the TXV, and where it's mounted, that's where we want to check superheat, because that's what that bulb is doing. It's maintaining superheat. So we want to check and make sure it's maintaining the proper superheat. So just go right to where the bulb is and put your temperature temperature clamp right where the bulb is located. Now we're going to tell you, we've got 90 degrees on our liquid line in heating mode, and we've got 300 PSI, and that's gonna, when we look at our chart on that pressure temperature chart, if we were to look at 300 PSI, that would tell us that our saturation temperature is 96. So we take that 96 minus the 90, and that'll tell us we've got 6 degrees of subcooling. The superheat, the suction line is 76. We would take that pressure and convert that to temperature. We looked at that chart, it's going to tell us that 76 PSI is equal to 19 degrees. Well, our line temperature, where the bulb is mounted, is 29 degrees. So we take that 29 minus the 19, and that'll tell us we've got 10 degrees of superheat. So 6 degrees subcooling, 10 degrees superheat. Now this chart would probably tell us we've got 6 to 12 on the subcooling and 8 to 16 on the superheat. So we would be right in the middle of that range. We probably would have not have even gotten to this point. We always want to check heat of extraction rejection first, mainly because that's going to tell us if we've got proper water flow. So that would have probably checked out, but if you were, recharging a system or something like that. And this will also kind of tell you, on a normally charged system, the source in 30 degrees, source out is 23.5. Normally we have about 7-8 degrees on a closed loop system on transferring of the heat, depending on your water flow. Obviously, water flow affects temperature difference. So if you've got high water flow, you're going to have low temperature difference, low water flow, high temperature difference, which can affect your superheat and subcooling as well. That's why we always want you to check water flow first. On an undercharged system, the condenser pressure, again, in this reservoir that we're using as a visual, undercharged, the reservoir level is going to be low. So even if that TXV adjusts the outlet at the dam all the way open, there's not going to be enough refrigerant flow out, because you don't have it stacked up behind the TXV. The result of that would be high superheat and low subcooling. So if we look at this example here, now when you're checking superheat and subcooling, sometimes it'll tell you check superheat first, subcooling. It doesn't really matter. You're going to check both of them anyway. It doesn't matter to me which one you check first. So in this example, we're in heating mode. So the warm side of TXV is in between our load heat exchanger and the TXV. Again, easiest way to know is just to grab that line, and there'll be a big temperature difference across that TXV. So we've got a liquid line, we're in heating mode, we're at 87 degrees. If we look at that 260 PSI on the pressure temperature chart, that'll tell us that it's 87 degrees. So we have no subcooling, and we go ahead and look at the superheat next. So we had 68 on our suction line pressure, which, if you've been in refrigeration for a while, you'd probably already know that 68 looks pretty low. That might give you an indication that you could be low on refrigerant, especially when you look at also your discharge pressure. But 68 PSI would convert to 14 degrees saturation temperature. So our line temperature was 29. So we take 29 minus the 14, that gives us 15 degrees of superheat. So we have, 10 degrees is what we're looking for on both, 10 and 10. So we have high superheat and low subcooling. That's an indication of an undercharged system on the refrigerant circuit. So basically, on an undercharged system in heating mode, you're going to have low subcooling. The pressure and the compressor amps are going to be low because you have low pressure vapor creating less load on the compressor. So an undercharged system in heating mode, you're going to have low discharge, low suction, high superheat, low subcooling, low airflow temperature or air temperature difference, low water temperature difference, and low amps in the compressor. You could also, the compressor could be hot as well. In the manuals towards our troubleshooting section, we will have a chart as well that will tell you if you have high superheat, low subcooling, what that means, if they're both high, what that means. So it'll kind of give you an idea of what to look for once you do get your superheat and subcooling readings. Undercharged in cooling mode, the evaporator is going to be starved of refrigerant, and the liquid level before the TXV is going to be low. So again, high superheat, low subcooling. You may have some frosting on an undercharged in cooling mode on the air coil, but it won't freeze the whole air coil up. If you ever walk out to a unit and the air coil in heat and cooling mode is one huge solid block of ice, that's normally an airflow issue. So if you ever see it frozen up real solid, that's probably due to a blower motor that's failed, a filter that's plugged up, or the air coil itself is plugged up. That's normally not a sign of low on refrigerant. If you see some like ribbons of frost across the air coil, that would be more of an indication of low on refrigerant. Sometimes you can see maybe a little bit of a condensation on the TXV or maybe a little bit of frost, but normally just condensation, good indication that it's undercharged. Overcharged. I don't see overcharged real often, mainly because if they're charging the system, they've usually done a repair or something like that, and the charge weight is listed right on the nameplate of the unit. If for some reason it's not on there, give me a call and I'll look it up and find out how much refrigerant's in it. But definitely makes it a little bit easier for especially some of the younger techs out there to charge up our systems. But an overcharged system, the reservoir level behind the TXV is going to be high. So basically the expansion device is going to just pinch it off to maintain proper superheat. So your superheat's going to be okay, but you will have high subcooling. The unit will run and it'll produce, but you're putting a lot more strain on the compressor. It's working a lot harder, and over time you're going to have problems with that compressor. It's going to run hot for too long, and then the oil kind of degrades, and then the compressor will lock up. So here's an overcharged system in heating mode. Again, the TXVs is going to store that excess refrigerant in the condenser, so it's going to back it up. It's basically shutting the gate off and stacking that refrigerant behind it. So again, we're in heating mode. Warm side of TXV is in between your load heat exchanger and the TXV. So if we had 325 PSI, we looked at our chart, that's going to tell us that's 101 degrees. So we take 101 minus 85, that gives us 16. So again, if we're trying for the 10 and 10, we already see, hey, we've got high subcooling. Then we take a look at our superheat, and it's 10 degrees. It's right where we want it on our superheat because it's pinching down, it's shutting that orifice off to maintain its superheat. But we will have high subcooling. So overcharged system, you're going to have reduced compression effectiveness. The system's going to have high compressor amps due to the higher pressure buildup on the discharge, and it also will increase your suction or your compression ratio, which is basically your discharge pressure divided by your suction pressure. So you will have high discharge pressure, suction pressure maybe a little bit high, but probably pretty close to normal. Superheat high, subcooling, or excuse me, superheat normal, subcooling high. You will have a little bit higher air temperature difference. The water side will be roughly the same, but you will be running a high compressor amps. If you run it like that way for a long time, you may notice the compressor is getting noisy. And that's because there's been damage done to the compressor due to the high amps and the high temperatures. Really doesn't really change a whole lot in cooling mode either. Everything's going to be about the same, except for the air temperature difference might be normal, but your water temperature will be high. Again, the superheat's going to remain constant, but the evaporator pressure can be expected to be normal to slightly higher due to overfeeding of the high liquid pressure. So we all are very, very guilty of this. You know, in the field, especially back in the day with the R22, we used to, you know, grab a hold of the suction line and charge the refrigerant until the suction line was beer can cold. And then you were like, yep, good to go. Basically, here's some temperatures that you might want to think about. At 140 degrees, you can't really leave your hand on the line. So a lot of times you touch that discharge line on the compressor, especially if you touch it like with your forearm or something, and it's going to burn you, you're going to jump pretty quickly. At 85, that's going to feel lukewarm to warm, you know, less than or greater than 85. Your surface temperature of your body is roughly 85, 86 degrees. So it may feel a tiny bit warm, or you know, almost like your body temperature. Less than 85 will feel neutral to cool. And the minimum temperature difference that you can feel using your hand is 5 degrees. I guess if you got 4 degrees, you're not going to feel the difference in the line. So just keep that in mind when you're feeling different temperatures. The discharge on the compressor will always be really hot. If you're checking like a desuperheater and you're wanting to see if there's temperature difference across it, you may not be able to feel that, because depending on where you're at in the seasons and what kind of water temperatures you're running, you may get only about 3 degrees temperature difference on that desuperheater water. So you may not feel a difference in it. So going throughout the circuit, this is what you should feel roughly when you're touching different lines. Again, the TXV, depending on what mode you're in, heating or cooling, you're going to be about 85 to 110. So if you're in heating mode, you're going to be between the TXV and the air coil. So you're probably going to be closer to that 110 degrees. On the other side of that TXV in heating mode, you're going to be at probably right around the 85 degree mark. So it kind of gives you an idea. You'll definitely be able to feel a difference in the line temperature between your TXVs there. Your suction line coming back to the compressor is always pretty cool or cold. And again, that compressor, the top of that compressor and that discharge line, depending on water temperatures and loads, is going to be 120 to 180 degrees. We won't cover that here. Filter dryer, whenever you're in the refrigerant circuit, I always like to throw this up there. Make sure we are replacing it. Never braze out a filter dryer. To be honest, you should never braze out any component from the refrigerant circuit. And the reason I say that is because I get parts back all the time that are unbrazed. I don't necessarily have a problem with unbrazing. The problem I do have with it is the fact that they're not using nitrogen when they're unbrazing. When you unbraze something, you're just brazing without the brazing rod in your hand. So once you do that, if you don't unbraze with nitrogen, then you're going to cause that black sludge that gets stuck on the TXV. Basically, it causes oxide buildup on the walls. The 410 with the higher pressures and the oil that's in it, it scrubs the walls more, and then your TXVs stick. So never torch out a component out of the system, and make sure you always replace your filter dryer whenever you're in the refrigerant circuit. It's one of my pet peeves is filter dryers and brazing practices. So performing the superheat and subcooling readings. We have straighter ports on the discharge and suction lines of the compressor. On a split unit, use those ports. Don't use the king valve ports. It can throw off your refrigerant readings. We get calls on that all the time where the tech calls in and we ask and we find out it's a split unit and we say, hey, go to the true discharge on the compressor and the suction. Basically, you can find the high and low pressure switches, and there'll be service ports pretty near those. So that's where I would always put my refrigerant gauges. Make sure that the temperature, the thermocouple that you're using, where it's mounted onto the pipe, is free of any insulation or glue. The sensor needs to be securely fastened and insulated from the ambient air temperature, and allow time for the sensor to become one with the refrigerant line. The sensor location for superheat is going to be the same for heating or cooling, so you don't have to change it anywhere. Basically, that TXV bulb is always monitoring superheat. So that's what you need to do. Look where it's monitoring superheat and go right there. So follow the bulb from the TXV, and that'll always be where we're checking superheat temperature. Subcooling, again, just remember it's the inlet of the expansion valve, but it's the warm side of the valve. I like to train in person because I like this. I like to throw the demo unit on right now and bring guys up and let them feel. It's I think it makes it a lot easier for the guys to feel things and put their hands on it, and it really clarifies things up a lot better, and they can actually see. But just remember the warm side of the TXV. That TXV on a package system is in the air handler section. So just remember that if you're checking your subcooling, don't put your temperature gauge on there and leave that door off because you'll go out on either low or high pressure depending on if you're in heating or cooling mode, because you're not getting airflow across the air coil. It's a negative pressure coil, so if you take the door off, the blower will pull out of the door that you've taken off rather than through the air coil, path of least resistance. If you do have to adjust charge, put a little bit of charge in and wait about 5 minutes and allow it to adjust and respond to the refrigerant that you've put in there. So we're going to go ahead and do some of these superheat and subcooling readings. We're going to measure the temperature of the suction line at the remote bulb location. So we don't want to use a thermometer like this. If that's all you got, that's not going to work. That's not a good way of doing it. Sorry about that. I don't know what happened to the other picture. I like to use a clamp on. A lot of meters come with a little thermocouple that you can unwind, and those work great as well. Just make sure that you tape it to the line, and then if you've got some insulation or something, wrap that thermocouple as well. Heating mode. So this is just a package system, pretty basic. We're going to check superheat first. Again, we may tell you to check superheat first in this as we go along, but to be honest, it doesn't really matter. But we're going to start with superheat. So again, we're going to measure suction line temperature, and that's where the TXV bulb is located, about a foot off the suction line on the compressor. So then we're going to take our pressure reading on our suction, and we're going to convert it to saturation temperature. Now, once we have that saturation temperature, we're going to subtract that from our line temperature, and that's going to equal our superheat. So we'll go through an example here. Cooling mode superheat, it doesn't change. Again, the bulb doesn't change. The only time that I should clarify for a second, the only time it will change is if you have a split unit. If you've got a split unit, then you need to go to the TXV that's in the air handler, because that's the cooling TXV. If you're in heating mode, you can stay down the compressor section. That's the only time it's really going to change. You could actually still check at the compressor. We would prefer you check a little bit closer to that TXV in your line set. But that's the only time it may change a little bit. Just because the line set, you could drop some temperature in that suction line before it gets all the way back to the compressor. So if you do happen to check it at the compressor and it's off, then you may want to recheck it closer to the air handler portion of it. But it's still pressure converted to temperature, and you're just doing the math. Again, heating on subcooling, warm side of TXV, and I've got that little line from the temperature on the wrong one. It should go up to the refrigerant line with the arrow, because that's the warm side of the TXV in between your load heat exchanger and the TXV. Again, you're going to measure your liquid line temperature. You're going to take your discharge pressure and convert it to temperature and do the math. It's not real difficult. The more difficult part is understanding what the reading means once you get it. Cooling mode, subcooling, again, warm side of TXV. Now we're going to be in between our source heat exchanger and our TXV. Now I tell you in between the filter dryer and the TXV, but I have seen where the factories put the filter dryer on the other side of the TXV. Normally, this is the side we put it on, but I have seen them reverse it at the factory. It's not really going to affect the system any, but I have seen them flip-flop it before. So just remember warm side of the TXV for our subcooling reading. And again, we're going to take our pressure, convert it to temperature, do the math, and that's going to give us our subcooling reading. Again, superheat range is normally about 8 to 12, so that's why that 10 number works so well. And subcooling is somewhere 4 to 16. Again, 10's right there in the middle. That works great. You can always look in the chart in the manual, and it will, give you a range, because we could actually be a little bit have wider ranges than this, but always double check the manual. If you don't have a manual, call tech support and we'll look it up for you. This is an example of one of the troubleshooting charts that's in the manual. These are lab conditions of different entering water temperatures, but it'll kind of even give you a range of what your discharge pressure and suction pressure should be, air temperature difference, water temperature difference, and obviously superheat and subcooling ranges. So we've definitely started putting these in the manuals to make it easier for troubleshooting in the field. So we'll go through some practice exercises on actually looking at the pressure temperature chart and doing some superheat and subcooling readings. So here we're going to be we're in heating mode. Again, it says we're going to check subcooling first, but it doesn't really matter to me which one you check. Here we are going to check subcooling first. So we're in heating mode. The warm side of the TXV is in between your load heat exchanger and the TXV. So we measure discharge pressure. It's 330 PSI. Now we need to, that's not a temperature. You can actually look at your gauge on your refrigerant and it'll tell you what that 330 is, or you can look at the pressure temperature chart, which we have here. So we had 330 PSI. So we follow that over and that tells us that our saturation temperature on 410 is 102 degrees. So 330 PSI converts to 102 degrees saturation temperature. So we measure our liquid line temperature near the TXV, and we're going to tell you that it's 94.3 degrees. So now we basically take our saturation temperature of 102 and subtract the 94.3. That gives us 7.7 degrees of subcooling. So that's only part of the equation, and you're thinking in your head, you know, John said 10 and 10. So 7.7, not too far off, doesn't look too bad. But we definitely want to move on and check the superheat. Again, superheat, we're checking right there where the bulb is mounted, about a foot or two off of the compressor. And again, that's going to be a cold line. So if we have suction pressure of 110, we can look at our pressure temperature chart. So we got 110, that's equal to 36 degrees saturation temperature. Our line temperature at our remote, at our bulb for our TXV, we're going to tell you that was 47.5 degrees. So we take that 47.5 minus our 36, and that gives us 11.5 degrees superheat. Yeah, we're thinking 10 and 10, looks pretty good. Now we can always look at the chart. So we had 70 degree entering water temperature, 3 GPM. That circle actually needs to be dropped down. We had to change a few of these slides, and I missed a few circles, so I apologize for that. But it's going to tell you that subcooling, it actually should be 7 to 12, and the superheat of 10 to 15. So we had 7.7, looks pretty good. Superheat of 11.5. So is the unit charged properly? Yeah. No issues, you know, with it. Now, if you have 65 degree entering water temperature, you're going to kind of have to look at the 50 and the 70 and kind of do a little bit of extrapolation. And you can probably figure that out, you know, what your kind of your range should be. So if you're outside of these ranges, we've gotten a lot better about not having such wide ranges of water temperatures, like 20 degrees. We've got it down to about, some units, we've got it down to 5 degree water temperature increments, but most of them are about 10 degree increments. So you can probably get a lot closer. This chart, I mean, we're looking at 20 degree increments, so pretty wide range, but most of ours now are the 10 degree, make it a little bit easier for you. So we'll go ahead and move on to another exercise. We're in cooling mode. So as you can see, the superheat reading is now in between your source heat exchanger and your TXV. Again, warm side of the TXV. Discharge pressure, 260. We now take that 260 and look at the chart. That 260 is not temperature, thank goodness. That 260 PSI is equal to 87 degrees. That's our saturation temperature. Measure our line temperature of 76.8. Then we can just do the math. 87 minus roughly 77. So we've got 10.2 degrees of subcooling. Looks pretty good. We're thinking of our 10 and 10 again. Next, we'll move on to our superheat. Again, superheat never changes. It's always right there where the bulb is mounted. If you look at the insulation on that suction line, you'll see a bulge in that suction line, and that's where the bulb is located. You'll see a little copper 1/8" tube running to it as well. Suction pressure of 130. Again, we got to convert that suction pressure to temperature. So we'll look at the chart. 130 is equal to 45 degrees. I know it's kind of circled at 135 and 47, and I missed that, but it's actually 45 degrees. So now we know we've got we know our temperature. We can just do the math. 57 minus 45 is 12.1. That, we're still thinking of our 10 and 10. So we would think, yeah, it's probably charged okay. We've got 10 degrees subcooling, 12 degrees superheat. We can always refer to the chart in the ILM as well. Subcooling, 8 to 14 and 10 to 16. So we were 10 and 12. So we're within our ranges. So the unit, yes, it is properly charged. You can also look at your water temperature differences, air temperature differences, and your pressures to make sure that they kind of all fall in line as well. So we'll look at another exercise here. We're in heating mode. We're gonna check subcooling. So discharge pressure 335. Convert that to temperature. So 335 is 104 degrees. That's really just a number right now. Look at our line temperature of 89.1. So now we take 104 minus our 89, and that gives us 14.9. That's our subcooling. Always check superheat as well. That's obviously subcooling is only one portion of the equation, of our diagnostic tool, I should say. Suction pressure is 74. We'll convert that 74 to temperature. Look at 74 on a chart. Tells us 74 is 17 degrees. Our line temperature on our suction line is 29.4. So 29 minus 17 is 11.4. So 11.4, 14.9 doesn't really sound too bad. But we'll look at the chart in the manual. Subcooling 6 to 12. Superheat of 9 to 14. So we've got our subcooling is high at 14.9, not super high, but a little bit, about 3 degrees roughly. And our superheat is okay. So in this situation, if our superheat's okay, that kind of tells us that we've got enough refrigerant to feed the TXV properly, but our subcooling is high. So we're stacking, it's telling us we're stacking up refrigerant behind that TXV. So we're overcharged. If we remember that reservoir level, it's just going to hold the excess refrigerant in the reservoir. So basically in the condenser, which would show up as high subcooling and pretty much normal superheat. So in this equation, the unit's overcharged. We'll do one more exercise here. We're going to check in cooling mode. Again, in cooling mode, we're between the TXV and the source heat exchanger. Discharge pressure of 310. We'll convert that 310, which is 98 degrees. Our line temperature is 94.3. So if we do the math on that, we've got, what, about 3.7? Yeah. 98 minus 94.3 is 3.7. You know, it already starts to make you think, 10 degrees, wow, we're definitely off from that. So we'll go ahead and move on to our superheat to see what it tells us about that side of it. Suction pressure of 120. Convert that to temperature. So 120 is equal to 41 degrees. Now we check our suction line temperature of 57.4. So take 57.4 minus 41, and we get 16.4. So if we're remembering, the rule of thumb of 10 and 10, we would say we have high superheat, low subcooling. Oh, you can always compare it to the manual if you've got a manual there. Again, we're in cooling mode. Should be 8 to 14 and 10 to 14. So we had 3.7 and 16.4. So is the unit charged properly? No. If we have low subcooling and high superheat, that will tell us that we're undercharged. Again, if you know what your superheat and subcooling is, in the manual, we'll have a chart that'll tell you what that means. Obviously, low subcooling, high superheat, you're undercharged. Normal superheat, high subcooling, then you're overcharged. If you have, there's a lot of different equations that are going to tell you if that TXV stuck open, stuck closed, not enough refrigerant, too much refrigerant, not enough airflow, that kind of thing. So you can look at your superheat and subcooling readings and kind of diagnose what's going on in the system. And it will show you in the manual what they kind of mean there. Here is basically the chart. So normal on both will be normal operation. Normal superheat, high subcooling, you're overcharged. High superheat, low subcooling, undercharged. If they're both high, you've got a restriction somewhere in the refrigerant circuit. More than likely, it's in the TXV. You could have maybe a filter dryer. If you have a good temperature difference across the filter dryer, that's where it probably would be. But normally, it's a TXV. And if they're both low, then you would have a stuck open TXV, which I don't see that very often. Sometimes if you file a warranty for a stuck open TXV, at least if I see it, a lot of times I'll give you a call just to get a little bit more information, just because I don't see that very often. And it's not, maybe the office just put the wrong code on there, which is fine. But I'm just normally confirming that that's the case on that. We do have this troubleshooting form. Again, it's in the manual. It'll list this little equation here. Superheat is equal to suction temperature minus suction saturation temperature. It'll tell you where to kind of look for your liquid lining heating mode and your liquid lining cooling mode. These are great troubleshooting charts. If you ever have any problems in the field, you're not really sure how to do the calculation, fill out as much information on this form as you possibly can, and then call us. That way, you don't have to run up and down the basement stairs 50 times talking on the phone to us when we ask for more information. These are located in every single manual. and they're very, very, very useful. So fill these out as much as possible and then give us a call, and we'll definitely help you out with your superheat and your subcooling readings. We do have a video on this that we've made, along with this training will be recorded. And I believe the superheat and subcooling calculations is already on YouTube. Matter of fact, I could hit play on it. That's the little YouTube play button. But we won't watch it today. But you can kind of see the refrigerant gauge there to the left. If you actually look at it, we're about 335 is the PSI on that. And if you actually look at the pink dial on there, where it crosses that pink dial, that's your temperature. So if you don't have a pressure temperature chart, you can look, and this one's got R22, R410, and R404. So just make sure you've got the right refrigerant that you're using. But this is about 104 degrees at 335 PSI. So you can use your refrigerant gauge for those temperatures as well. So that's what I have for today. I'm not going to ask you any questions or anything. If you definitely have questions, feel free to ask. And don't be afraid to give us a call and tech support with your superheat and subcooling readings and what they mean. We deal with them every day, so we do it all the time. Some guys don't necessarily understand the superheat and subcooling, what they really mean. So don't ever hesitate to call tech support, because that's what we're there for. And that's all we do all day long. So with that, if you have any questions, feel free to ask. If not, I believe I have a reversing valve training on Thursday. It probably won't be real long. It's just going to talk a little bit about the workings and how to diagnose it and how it actually operates. So feel free to join in. And with that, I thank you guys for sitting in, and we'll talk to you soon.